that you've got an X bar here in your first sample. Will you reject or fail to reject the null hypothesis?
Based on just one sample?
Yeah, you do a sample and you find an X bar and it's in your rejection region and therefore you reject the null, right?
Mm-hmm.
Okay. What would then this shaded area be? In white.
Just telling James how well this was going.
And it is. Swimmingly. Well, first of all, is this under the null or the alternative distributions?
Alternatives?
The null.
The null,
Right? Okay, so under the validity of the null hypothesis, it is, well, it's an area, so it has to be a probability. The probability of getting a test statistic this large or larger, right? Okay, larger than this is considered more contradictory to the null hypothesis than this particular X bar. Does everybody understand that? Okay, so it is the probability under the validity of the null of getting a test statistic as or more contradictory to the null hypothesis than the one you just got. That's the definition of a p-value. And it's also called the observed level of significance. Now, let's look at another possibility. Let's say you did got a different sample here. Would you reject or fail to reject the null? You would fail to reject. And again, the p-value would be everything from here to the right. So, let's look at the p-value. Right here, it's the area that's shaded red. Is it larger or smaller than alpha? Smaller, yes? What's happening if we move the sample, the test statistic to the left? What's happening to the p-value? It's getting larger, right? P-value is getting larger. So, and in fact here, is it larger or smaller than alpha? Larger. Okay. And what about right there? Exactly. So there's a relationship here between the p-value and alpha that is one-to-one as to whether or not the critical value of the test statistic is greater than or less than the critical value. And so you've got that if, so X bar is in, by the way, this needs element up, in the rejection region, then you also have that the p-value is less than alpha. If X bar is not in the rejection region, then the p-value is greater than or equal to alpha. And in either of those lead you to here, reject the null, or here, fail to reject the null. These are one-to-one. You cannot make, make one decision based on p-value and draw another conclusion based on your test statistic. They're one-to-one. It's just a question of, are you looking at points along the real number line or area? And the reason people like the p-value, even though it's a pain to calculate, is that once you've done this a while, computers will just spit out p-values. And then you're done, because there's no work in selecting alpha. That's just a number you come up with, right? Whereas when we do traditional hypothesis testing, we have to choose alpha, we have to find the critical value, which gives us the rejection region, calculate the test statistic, and decide then whether or not the test statistic is in our rejection region. So it's more work. It's more straightforward, but it's more work. Okay, so the thing that you have to remember is p-value less than alpha, reject the null. All right. we can use. They always start with determining the hypotheses, figuring out which test statistic to use. In our case, it's either going to be z distributed or q distributed. Specify alpha. Then we're going to come up with a decision rule, collect the sample, compare x bar. We're either going to calculate a p-value or we're going to look at the rejection region in order to conclude. But in general, I like to cut this down to 4 steps that are always the same and may always be applied. First, you set up the null and alternative hypothesis. Second, you come up with a decision rule. Specifically, you find the rejection region. And it's done before the third step, which is to calculate x bar, or more particularly, the standardized test statistic. Typically, what I'm going to want is the standardized test statistic, which is x bar minus mu0 over either s of the square root of n or sigma of the square root of n. And then only as step 4 do we conclude. And typically, you want to conclude in terms of the problem, because that'll bring it back to a business application. Okay, so with one-tailed tests, large sample, notice that you're a z regardless. The only difference when sigma is unknown is that you estimate the standard deviation. The hypotheses are identical, the conclusions are also identical, except that you have a one-sided rejection region. We'll look at an example of that shortly. So in our particular application, the alpha 5% led us to look in either the bottom row of the t-table or the z to find that our critical value is going to be 1.645 standard deviations above the mean. And notice we can do that before we collect any data. When we do collect data, from 40 observations, we find a mean of 13.25 minutes and a standard deviation estimated to be 3.2 minutes. So plug that into our standardized test statistic formula, or z-value, you end up with 2.47 standard deviations of x bar above the mean. And you know from the empirical rule and elsewhere that 2.47 is quite a bit. In fact, we find that 2.47 is greater than 1.645, and we conclude that the mean time of response is greater than 12 minutes. And we do so with a 5% alpha, which means that with our methodology, we're only going to conclude incorrectly, and we're only going to have type 1 errors 1 in 20 times. Questions on that? Okay. The other thing we can do then is to look at the p-value. So we know the p-value is less than alpha because, well, we rejected the null. When we looked up 2.47, you will find literally the area to the right of 0 and to the left of 2.47. If you look this up in the z-table in the 9th edition, you look it up in the 10th edition, you'll find 0.5 plus that. And this piece is found to be 0.068 by subtracting what you looked up from 1. So it's the probability of getting a test statistic as contradictory or more contradictory to the null hypothesis than the one you got, if the null is true. So if we think about that, what it's saying is, if the mean response time is 12 minutes or less, the probability that we would see a mean response time in our sample of 13.25 minutes or more is only 0.0068, which is quite small. And basically, one way to think about that is, and it's completely wrong, but you can think of the p-value in some sense as the probability the null is true. Remember, the null is either true or false, but as a memory help, it's not bad. A very small number there will lead you to reject the null hypothesis. Okay, and for a large sample case, notice there is no difference, well, there's a difference in the hypotheses, but there's no difference in the standardized test statistic. The only difference here is now you're rejecting the null for large sample and small sample. I'm sorry, for left tail and right tail. Okay, as an example of that, think about toothpaste. If you overfill your toothpaste, you're wasting money, right? If you underfill your toothpaste, you're cheating your customers. Neither of these are good. So you want your toothpaste fills to be spot on, or at least pretty close, right? Okay. You're going to sample 30 tubes, and typically when you test these, that would mean that you're destroying them, so you don't want to overdo this. And essentially what you want to do is keep measuring how many ounces of toothpaste are in the tubes on average. So is this a research claim or manufacturing style hypothesis test? Manufacturing, and therefore the null hypothesis is going to be ongoing. There you go, right? Because either way it would be wrong. Would mean you'd have to recalibrate. So your null hypothesis, everything is fine, which means you have equality. Yes? Okay. And we're going to test that at a 5% level of significance. In that case, you're going to reject then if you get a standardized test statistic greater than 1.96 or less than minus 1.96. And that's what this looks like in the picture. Notice so far, we have no data. So we're at step 2 in this process. All we're saying is if we get any numbers down here or up here, that will lead us to conclude that the machine is either underfilling or overfilling the toothpaste. Notice also that at 5% level of significance, each tail only has half of that, 2.5%. All right, so let's say we did our sample of 20, we found a standard deviation of 0.2 ounces, and X bar was 6.1. We find that our standardized test statistic is 2.74. That's greater than 1.96, right? Yes? So we conclude that the machine is no longer filling the proper amount. It's filling too much. Now, one natural question here is, can we conclude that it's filling too much? Or can we only conclude that it's filling something different than 6 ounces? That would be a very logical conclusion, except that it turns out that if you're able to reject a two-sided equality in a two-sided test, you're always able to reject in a one-sided test. So if you're able to reject a two-sided test, you're also able to say that we're overfilling in this case. But normally I'd agree with you that it's best to be conservative. Okay. We also can look up our 2.74 and find that on the one hand we've got 0.031 in the tail beyond 2.74. We should probably draw this. So we have 2.74 here. This is Z. But remember, you can get a number of minus 2.74 as well, and numbers that are further away are considered more contradictory to the null. And therefore, both of these shaded areas are half the p-value. Okay? And that's why you need to multiply that by 2 in order to get the full p-value. Okay? All right. Should probably do a problem. Yeah, perfect time. All right, so we'll do a problem 62 for a large sample. So here we've got the population mean salary of public school teachers in the state of New York is known to be $45,250. So what symbol should we use for that? It's a mu, but it's going to be used subscripted mu 0. And we take a sample of 95 teachers in New York City, and we find, based on that, that they have a mean salary of $47,000, and we're also told to use a population standard deviation of 6,300. How is it that we know X bar is normally distributed? Sample size is greater than 30, which means we can use
Central limit
central
theorem.
limit theorem, and that's why we can treat X bar as normally distributed. Good. Okay. What is the mean of the distribution of X bar under the validity of the null hypothesis? Where is this distribution centered?
45,250.
45,250. Very good. A lot of people attempted to put the sample mean in the center, but that makes no sense because the sample mean is drawn, soon to be drawn from this distribution. Okay. The first thing we're asked to do is formulate the null and alternative hypotheses to determine whether the sample data support the conclusion that public school teachers in New York City have a higher mean salary than the public school teachers in the state of New York. Okay? Sure. Formulate the null and alternative hypotheses that can be used to determine whether the sample data support the conclusion that public school teachers in New York City have a higher mean salary than the public school teachers in the state of New York. So the positive statement you want to make is public school teachers in New York City make more.
So the null would be means less than 45,250. Less than or equal to.
Perfect. Is everybody happy with that? And that is it research or manufacturing?
Research.
Research, right? Just one's off. So what's the alternative?
Means greater.
There we go. Okay. Second thing, we're going to do this both ways, both the traditional and the non-traditional, or with the p-value. We're in C, we're told to use an alpha of 1%. So that's going to tell us where the cutoff is. Now, if we get an X bar down here, is that consistent or inconsistent with the null? It's consistent, so we're not likely to reject the null hypothesis if we get an X bar down here, yes? Everybody see that? Even if you got an X bar of $10, you wouldn't reject the null hypothesis, right? The null hypothesis is that X bar mu is less than or equal to 45,250. Any number less than 45,250, you wouldn't even bother with statistics. Because there's no way that this data would ever convince you that mu is greater than 45,250 in that case. So the cutoff is going to be up here. Yep.
Backing up a bit, just on the way we approach the problem, if we're trying to see if they make more,
Right.
why are we testing for if they make less?
Ha. So glad you asked. Because the positive statements we can make depend on the structure of the hypothesis test. So with this structure, we either fail to reject this statement, or we reject this statement and conclude that New York City school teachers make more. If we did it the other way around, the only thing we could say was that we fail to reject the null hypothesis that New York City school teachers make more, or we reject the null and conclude that New York City school teachers make less. But we're asked to show that New York City school teachers make more, not fail to reject the idea that they make more. So it depends on the formulation of the problem. So how does the 1% alpha give us that cutoff? We agreed that the cutoff is somewhere up here, right? Where's alpha? Where's Nemo?
Figure out its Z-score.
In the tail.
Well, but in the tail, right. So this is alpha, and it's 1%. So use alpha to get the z-score, not the other way around. Now, if this is 1%, what is z? You either look in the bottom row of the T, or in the body of the table in the Z, and you find how much? Very good. So we want something that's 2.326 standard deviations greater than 45 to 50. But in terms of Z, we have the critical value is 2.326, and the rejection region is 2.326 to positive infinity. Now, what about in terms of x bar? Remember, what follows is not my preferred approach, but just so you have, you can choose pretty much whichever way you want to do it. Well, the critical value in terms of x bar is mu sub 0 plus z sub alpha times sigma over the square root of n. So that's 45 to 50 plus 2.326, 6300 over the square root of 95. And naturally, this one I never wrote down, so I think we have a calculator here. Add that to 45250, 46753. Okay? So in terms of rejection region for x bar, that's 46753.45 positive infinity. So in terms of this, we know x bar is equal to 47,000. Is that in the rejection region?
Yes.
Yes.
Equal.
Which means we reject the null hypothesis and conclude what? If we translated this, so this was step one.
No. I'm sorry, James. Can you repeat that? Couldn't hear James.
Oh, consistent.
Based on our sample, the teachers in New York City think more than the teachers in New York State.
So the basic idea is we reject the null hypothesis. We conclude that New York City school teachers have a higher mean salary than the mean for public school teachers in the entire state of New York.
And we did that by rejecting that they have less than or equal to.
Precisely. Precisely. Okay, we can do the same thing by calculating the standardized test statistic, which is x bar minus mu sub 0 over the standard error. So that's 47,000 minus 45,250 over 6,300 divided by the square root of 95, which is approximately 2.707. Is that in the rejection region? And remember, now we're looking at this rejection region, right? Rejection region in terms of Z.
Mm-hmm.
Yes, it is. So we again reject the null with the identical conclusion. Now, just for fun, we are going to do the same thing for using a p-value. So what can you tell me about p-value? It will be less than alpha, and since alpha here is 1%, it's less than
1%.
1%, right? So let's say that this is x bar equal to 47,000, and the standardized test statistic is 2.71. So we're interested in that area. We look up 2.71, what do we find? Well, if you have the 9th edition version, this piece here is 0.4966, which means that the p-value is equal to
0.034.
0.5 minus 0.4966, or 0.00364. And you'll notice that that is in fact less than alpha, which leads you to reject the null. It doesn't matter which approach you use, you're always going to get a consistent answer. If one of them leads you to reject the null, they'll all lead you to reject the null. It's just that one looks at the real number line according to this scale with x bar, one according to the scale of the standard deviation for x bar, the z-scores, and one looks at the areas. Questions on that?
What just not about the problem, but the shorthand you're using, the little E symbol.
Oh, that means element of. So 47,000 is an element of the rejection region. It just means it's in the rejection region.
Okay.
Other questions? Okay. What's that?
Hold on, I gotta.
All right.
C1,
Now, 3 is this. And, right, we have two different 3s depending on if we use x bar as the standardized test statistic. And then this part is the conclusion here.
Is there a clue telling us which method of reaching our conclusion we want, or is it pick your poison and go with that?
In this class, I'll let you know. My preference tends to be either p-value or in terms of standardized test statistic. In real life, pick your poison.
Okay.
Whatever makes you happy. Typically, people find one thing that sort of feels easier than the others, and you just stick with it. Okay. In that case, we really have a choice to make. Do you want a short break now, or do we power through? Either way will work. It sort of depends on your saturation levels.
I could use some cooling off time.
All right, let's take a 5 minute, 8 minute, 5